Welcome to our lessons on ordinary differential equations. In this lesson, we are going to look at application of first order differential equation. That's what we're going to look at on this series of videos. And we want to start with linear models. And for this video, we'll be going into population growth and decay. Now, in the application of differential equation, we are concerned with more than just solving a particular initial value problem. The complete solution process consists of the following three steps. 1. Construction of a mathematical model. In the construction of a mathematical model, the variables involved must be carefully defined and the governing law identified. That's what I mean by we just have to, whenever you are given a problem, a real life problem, you have to identify the variables to be able to come out which of them is a dependent variable, which of them is an independent variable. Then we do to look at how the variables are related. Those are what I mean by the governing laws. And the mathematical model is then some equation represent the idealization of the physical laws, taking into account some simplifying assumption in order to make the model tractable. So what it is that the mathematical model you're going to come out is actually going to be an equation that is relating the variables that is supposed to take into account the idea that is being presented and all the assumptions that will make the model work. Solutions of the mathematical equations. When permitted, exact solutions are usually determined, but in many cases, one must rely on approximate solution. In fact, in some real-life situations, it is difficult to get exact solutions, so you can analytically solve the problem, but you have to resolve into numerical. But in this very lesson, we are going to limit ourselves with problems that will be solved analytically, that have exact solutions. The third is the interpretation of the results. When the results are obtained, after you model it and then you solve, then the solution should be consist of physical intuition and physical evidence. And if a good model has been constructed, the solution should describe many of the essential characteristics of the system under the study. So here, when you get the results should meet and should be consistent with the problem, and should be able to describe majority of the characteristics. If you have recalled your knowledge in linear regression, you need to test what percentage of the data can the model explain, and that is where we are talking about. So these are the three things you need to consider when looking at the model. So without wasting time, we jump into population growth and decay. You see that the growth rate of a population, that's the change in population, where N of t is the population size at the time t, depend on 1, the birth rate, and b, the mortality rate m, both of which will vary in direct proportion to the size of the population. So these are the two things that determine the population or the change in population in every environment. There are others, but we are going to limit ourselves to a very simple case. So we have the like migration rate, both migration and migration out. They are also part of the population variability or changes in the population within a certain system. Population and growth problems have similar differential equations or models as compared to the radioactive decay problem. In the population model, the rate of change of population P is proportional to the population at any time T and is given by dP dt is proportional to P. Similarly, the radioactive substance decays at a rate directly proportional to the amount Y present and is represented mathematically as dy dt proportional to Y. So if you check the two models, you realize that they have the same thing, only that there are differences in increase. Mostly in this one, the gradient increases, but this one, the gradient is negative, positive, and this one, the gradient is negative. Those are the only difference between the two of them, but they are all the same. If P equals to P of t is the population and the initial population P of 0 equals to P naught, then from dP dt proportional to P, we can introduce our equal sign and then introduce the constant of proportionality, which in this case the R is the birth rate. In fact, we want to look at a very simple case of just the birth rate being the only factor. We want to look at it from that point of view. So R is the birth rate, and then with the initial population P of 0 being equals P naught, we are going to have the IBP as dP dt equal to Rp with P of 0 equal to P naught. So with this, we can solve the population model. And this equation here is separable. So we are going to have dP dt equal to R dt. So if you integrate both sides, you're going to have ln P equal to RT plus ln C. So we are going to have P to be equal to C e raised to the power RT. Now with the initial population of P of 0, that's at time t equal to 0, we're going to have C times e raised to the power 0 and is equal to P naught. So that means our C is equal to P naught. And for that matter, we can say that our population P of t is equal to the initial population times e raised to the power the birth rate times time. And this is a simple case of the population model. Similarly to the radioactive decay, we can also say that our dy dt equal to ky, and we separate the variables, and with the initial value of y of 0 equals to y naught, this equation 2 is separable, and I'm not going to go through it. So the solution is simply the same as y naught e raised to the power kt. So they have the same model as the population model. So let's begin with an example here. The population of a particular community is observed to increase at a rate proportional to the number of people present at any one time. In the last 5 years, the population has doubled. How many years will it take for the population to triple? So here we are saying that dP dt is proportional to P, and therefore we are going to have dP dt equal to Rp, and we were not giving the initial population. We are going to say P of 0 equals to what? P naught. This becomes our RVP. Now the further information that we have been told is that in the last 5 years the population has doubled. So that means P of 5 is equal to 2P naught. So this is the further information that we have in the population model. So we already know the solution to this. So we solve this, we know you're going to get P of t to be equal to P naught e raised to the power RT. We have been told that after 5 years, when t is equal to 5, the P of 5 becomes 2 times of the initial population. So we can say P of 5 equals to P naught e raised to the power 5R is equal to 2P naught. So solving this, the P naught to cancel it, just then have e raised to the power 5R equal to 2, and taking the ln of both sides, we're going to have 5R equals to ln 2. Therefore R is ln 2 over 5, which when solved, we are going to get 0.1386. So that is a rate, the birth rate. So our P of t can now be written as P naught e raised to the power 0.1386 t. So that's the population model. Now we are being asked how many years it will take the population to triple. So we are looking for where P of t equals to 3P naught. So we just equate that one to this. So we are going to say that P naught e raised to the power 0.1386 t is equal to 3P naught. Therefore the P naught to cancel each other. So you have U of 0.1386 t equals to 3, and therefore 0.1386 t equals to ln 3. That's we are taking the ln of both sides, and therefore our t is going to be 7.9, approximately 7.9. So we are saying that it will take about 7.9 years for the population to triple. Let's look at our third example. Initially, 100 milligrams of a radioactive substance was present. After 6 hours, the mass has decreased by 3%. If the rate of decay is proportional to the amount of the substance present at time t, find the amount remaining after 24 hours. So here, we have been told that initially, that's y of 0 is 100 milligrams. Then, we have been told that after 6 hours, it is only 3%. 3% has been decreased by 3%. That means that 100 minus 3% of the 100 milligrams remains. That will be 97 milligrams remaining. So the model we know is dy dt equal to ky, and the y of 0 is 100, and we have been told that y of 6 is 97 milligrams. So these are the information we have in the question there. We know that when you solve this, you are going to get y of t to be equal to y naught, which is 100, e raised to the power kt, because you are using k here. This is the decay, e raised to the power kt. Now with the 6 here, we have been told that y of 6 is 97. So we put them in to get our k. So y of 6 is go to 100 e raised to the power 6k, and this goes to 97. So e raised to the power 6k equals 0.97, and therefore 6k is ln of 0.97, and therefore our k is going to give us negative 0.00508. So that is the population. So in that context, that's the k, sorry. So p of t can now be written as 100 e raised to the power negative 0.00508 t. And the question is to find the remaining amount after 24 hours. So we just need p of 24, which is going to give us 100 e raised to the power negative 0.00508 times 24, and the answer is 88.52 milligrams. Let's look at our next example. The population of insects in a region will grow at a rate that is proportional to their current population. In the absence of any outside factors, the population will triple in 2 weeks' time. On any given day, there is a net migration into the area of 15 insects, and 16 are eaten by the local birds population, and 7 die of natural causes. If there are initially 100 insects in the area, will the population survive? If not, when do they die out? So let's look at the information here. The number of insects that might migrate in this context is 15. So we say 15 per day migrates. The number of insects that are eaten in this concept here is 16. So 15 migrates in, they come in, and then 16 insects are eaten every day. And then the number of insects which dies is 7. So these are the informations we have there. So if you want to compute the rate of change of the population of the insect, we are saying that the dp dt is actually equals to rp plus 15, that's those which are migrated in, minus 16, those which are 18, minus 7, those who dies. So we are going to have dp dt is equals to rp minus 8. And if you go back to the question, you have been told that initially 100 insects were present. So that means that p of 0 is equal to 100, and this is the IV. But there's a further information in the question. In the absence of any outside factor, that means when these factors and these factors were not in play, the population tripled. So we want to look at that one first before we go. But this is the model we are going to solve. But let's look at. So in the absence of any outside factors, that means no migration, nobody is eating, nobody dies. Our population model will have been dp dt equals to rp with p of 0 equal to 100. So based on this, we can get our r. So when you solve this, you know p of t is going to be 100 e raised to the power rt. In the absence of any outside population, the population will triple in 2 weeks. So that 2 weeks is 14 days. We have been working around 14. So p of 14, which is 100 times e raised to the power 14r, is equal to 3 p naught. The population will triple. 3 p naught, and our p naught is 100, so you're going to get 300. So e raised to the power 14r is going to be equal to 3, and therefore 14R equals a length 3. And when you compute our R, we got R to be 0.0785. So that's our R. So based on that, we can come and put the R back into this model. And the model we are supposed to solve, the IVP, becomes P prime, which is the PDT, equal to 0.0785 P minus 8, which with P of 0 being equal to 100. So that is what we are going to solve right now. So to solve this is a first order linear equation. So I'm going to use the integrating factor. P naught is 100. The integrating factor mu of t is e raised to the power integral of negative 0.0785 dt, which is going to give us e raised to the power negative 0.0785 t. So the population at any time is going to be the integral of negative 8 times e raised to the power negative 0.0785 t dt plus c, which is a constant, divided by e raised to the power negative 0.0785 t. So with this, when you solve this, you're going to get 101. If you integrate it, this will give us this, we divide by this. We're going to get 101.91 plus c e raised to the power 0.0785 t. So that is our destiny. Now p of 0, you're going to get 101.91 plus c e raised to the power 0 equals 100. So c will become negative 1.91. Therefore, our population at any time become 101.91 minus 1.91 e raised to the power 0.0785 t. So that's the population model. Now, if you look at this, the question is asking us whether would the population die. Now, this is exponential. This very number here is positive. The exponent for this is positive, so that is going to cause an increase. But the coefficient is negative, so it means that you're going to be subtracting from this. So that means that at a certain point in time, the population will die. So we can conclude that the population will die since the coefficient, this very coefficient of the e raised to the power 0.0785 t is negative. So the population will die. If the population will die, when will it die? It will die when the population is 0, right? So it's going to be going to equate this one to 0 and solve. So p at the time the population will die is going to be 0. So we're going to say 0 is equal to 101.91 minus 1.91 e raised to the power 0.0785 t, and this will give us e raised to the power e raised to 0.0785 t to be equal to 53.35. I will subtract, we change this one here and then divide by 1.91, 53.35. And when we solve it, we are going to get, we are taking the lane of both sides, that will be 0.0785 t equals a lane of 53.35. T is going to give us 50.66. 50.66, if you divide by 7, t in weeks, if you divide by 7, you're going to get 7.2 weeks. That's approximately 7.2 weeks. These are our approximate value. So we say that the population will die out in 7.2 weeks. Let's see how this one looks like in the graphical representation. This population model, how it's going to die out. Okay, so if you look at our model, I've created a slider here. The slider is this, and I've given the maximum distance of 50.66. That's the maximum, 50.65, maximum 50.65. So we want to see how this thing will draw. So we trace this one. So we trace it, and then let me animate, and let's see how this. So we start from 100, and as our time goes by, the population decreases. So where the dot coming down is the decrease in the population until it gets to the 50.66. So if you look at this, that's how the population is the highest of 100, and then it decreases down to this ground. Thank you for watching. We are going to meet again.